So Keith is a mathematician working for British Telecom, or sorry, for BT. I do apologise, and he's going to tell us about the FFT and finite group theory. Over to you, Keith.
Thank you. Yeah, I really enjoyed all the caustic remarks in the previous talk, but I don't have that kind of thing. Yeah, I mean, Chris was right at the beginning when he said that your phone is doing about 1,000 FFTs per second. In fact, it's exactly 1,000, and they're very big ones. And so I want to fill in some of the background to that. And my point will be that if we could develop even smarter versions of FFTs, we could get better performance out of our devices, phones and laptops, and every device with a wireless connection is doing these FFTs all the time. And I will give some of the background to that and say where the group theory comes in. So very crudely, the wireless communications systems work by this thing called a protocol stack, where there's a copy of it in every transmitting device and every receiving device. And it's a sequence of digital signal processing steps, essentially, which are done in the digital domain, so they're exact. And at the bottom of the stack is the physical layer, which is the wireless link, which we're trying to use to send information. And this is the weakest link in the chain by far. It's an analog channel. It's a noisy channel. It has interference. So where the FFT comes in is right at the bottom where those curved arrows are. So if you're transmitting, just before you generate that waveform, you do what is usually organized, so you do an inverse FFT there and a forward FFT on the receive side, but it's essentially the same thing, really. So I have to explain a bit why the FFT comes in at all. So the FFT is a computationally fast way of computing a discrete Fourier transform. A DFT, what is that exactly? It's a matrix vector multiplier where the matrix has this structure. You start with a root of unity. If we're doing n dimensions, we take an nth root and we set the matrix element ij to the omega to the I times j. And it's a scaled unity matrix. Usually the engineers don't put the scaling of 1 over root n, which is in my third bullet point. They do the scaling on one side only, so it's a scaled unitary matrix. And in the bottom line, I've introduced this star-star notation for a kind of element-wise exponentiation. And the point here is to show that it's the pattern of integers in this square matrix that's the essential point about this matrix structure. Everything that works by the FFT achieves that by essentially exploiting the structure in that pattern of integers. So even though it's a complex matrix, it's only these integer exponents which really matter. So that's a DFT so it's not yet a fast one. The fast one, well, a bit of history, because other people have been giving that, can be traced back to Gauss in the early 19th century, and really got going in the 1960s when it was really needed in signal processing. And here's a simple way to understand what's happening for the 4-dimensional DFT. Essentially, by introducing a permutation matrix, this capital Pi, and a simple diagonal matrix, then we've reduced the 4-dimensional DFT to essentially a 2-dimensional one, F2, and these scalings and permutations, which computationally cost nothing. So that's how the speed up in the computation is obtained. A general form of that idea is expressed in this result by Cooley Tukey, the main developers of the FFT in the 1960s. So if you're doing an n-dimensional transform and you can factorize it, so it's not a prime n, factorize it in any way you like, p times m, then here's the reduction of the n-dimensional FFT to some lower order ones, well, p order and m order, and some permutations and some diagonal blocks, and there are explicit constructions of these pi's and omegas. Anybody wants more background, I highly recommend the classic Van Loon textbook on the topic. Everything is there. So here it is written out explicitly for n equals 6. And well, actually it happens, if we factorize 6 as 3 times 2, that's the only sensible factorization, then 3 plus 2 plus 1 is 6. So in fact, looking at the bottom line, we haven't reduced the number of operations. So there's no saving in this case. Operations, by the way, usually we just count multiplications because the number of additions is of the same order. So this is the computational complexity that we're interested in. How does the number of operations required to compute the n-dimensional DFT scale with the with n? And it turns out with the FFT, it's n log n. And not n squared, as it would have been if the FFT algorithm didn't exist. Just to show how simple that is, here's a complete general implementation in Python. It's recursive, so it calls itself for the lower dimensional transforms. And yeah, for today's homework exercise, you're asked to rewrite this so the two for loops don't exist by using better exploitation of vectorization or broadcasting of array structures. You can do it in numerical Python like this is, or MATLAB, or whatever you like. But even better would be to get rid of those two for loops. Now that's my 5-minute introduction to what the FFT is. And now we have to ask why it comes up in wireless communication. So the way we transmit information is to have a set of subcarriers, which are individual sine waves at a narrow spacing, equal spacing. In fact, they're orthogonal to each other, which is important. And on each subcarrier, we introduce a modulation, which is actually the information carrying part of the story. So the symbol X, or XK, is going to be the symbol transmitted on the kth subcarrier. And a symbol means it's generally a complex number where we map the bits we want to transmit onto the complex plane. And typically we might say map 2 bits onto 4 points in the complex plane, or 3 bits onto 8 points in the complex plane in a regular square array. And this is called quadrature amplitude modulation. And so those complex numbers x are multiplied by the exponential function you see in the sum, because that's the sine wave, which is the subcarrier. And the total transmitted signal is the sum of those, sum of all subcarriers. And so if you look at that, it is in fact a discrete Fourier transform. It's nothing more than that. So that is why the DFT comes into the communications problem. It gives us a way of generating the signal we want to transmit out of all of the symbols that we're going to transmit on all those subcarriers simultaneously. And generally what we do is we have time slots, typically 1 millisecond, where we transmit that signal SJ for that 1 millisecond, and then the next millisecond time slot, a new set of symbols comes in and we start all over. So that's why there are 1,000 FFTs per second on your phone. So this is really the core of the idea. If the FFT algorithm didn't exist, we wouldn't be able to compute that sum fast enough on a phone to transmit 1,000 time slots every second. So that is that's how the DFT and the FFT come into signal transmission. And this is, if you just want to see what the power spectrum of such a signal looks like, you could take it to be this red curve, or the blue is an alternative one. So this is the power spectral density. The x-axis is frequency, and the great advantage, so this was 16 subcarriers, we actually use a lot more than that. The great advantage of this form of transmission is that the signal occupies very largely a rectangular block of spectrum, and in the real system that would be a block of spectrum, for example, 10 megahertz wide at center frequency 3.5 gigahertz, which has been licensed to us by Ofcom, and we're not supposed to transmit outside that. Now you will see these drop off outside, which is signals which are getting weaker and weaker as you go away from the center frequency. They have to be kept below certain limits because they'll be interfering with other network operators. So we can control all these things by filtering and by using the appropriate number of subcarriers. More subcarriers, in fact, will reduce those side lobes. Now, so that's the conventional picture, and this is how we transmit. So you think now of the base station transmitting in this 10 megahertz channel to lots of users simultaneously. How is it going to divide up the spectrum with a bit for each user? And the way it does it is this thing called the resource block grid. Maybe this picture is not very useful. I think I'll just go direct to this simpler one. So along the bottom here, you see the complete 10 megahertz channel. And that's my phone at the top. And my phone has been allocated these dark blue sections of the frequency domain. That's decided by the base station, depending on how much resources I need. And you notice they're not equally spaced, and they're not even necessarily of the same width. I mean, these two together essentially form one larger chunk of spectrum. So the idea here is my phone only needs to do an FFT on these 5 blocks. It can ignore the rest because it doesn't contain any information for me. In fact, the simple way is you just do a FFT across the whole frequency band, and that might be typically 1024 if you're using 2 to the n subcarriers. All the other computations are wasted, the ones that operate in the white areas, and they use battery power. That's probably the most significant thing. This is a heavy computation. It drains your battery, and we're wasting battery power decoding things which are not intended for us. Now, if you're worried about security, you know, maybe I'm hearing somebody else's voice call or something. That can't happen because of the encryption which is applied before this FFT processing is done. So there's no worry there. It's just that I don't want to do FFT on these white bits. They're not for me. So this is where I want to pose a challenge to the group theory experts. I've done this before on one or two other presentations and not got any good ideas yet. So I'm still trying. Yeah, so what I did is I worked out some small cases by hand just to see how it goes. And if you were doing n equals 6, but you only wanted to do the outer 2 blocks of size 2, and the middle 2 were not for me, then that they're indicated in red. And so all you have to do is delete some rows or columns before you do the multiplications. So that's simple enough. You get the same answer, but you've done less multiplies and additions. My question is, and this is where the challenge to the pure maths comes, the last point I want to make. Can you write down a general form of this that works for an arbitrary pattern of these blue blocks, possibly scattered over the frequency domain in a complicated way? Is there an algorithm which will detect, well, it knows where the blocks are, but it will generate an algorithm specifically for that block layout that's optimal in terms of minimizing the number of operations. In other words, it will compute as fast as possible. And if there is going to be such a thing, it might be based on some known algebra. For example, in this classic paper by Nicholson, which again I highly recommend, it's one of the earliest and still one of the best. He writes down a general form of FFT. I don't know if it's general enough for what I'm proposing, and I don't know if it can be turned easily into an algorithm that just computes rapidly. There might be overheads that I don't realize in using this method. So that is my my final point. I think, how's my time going?
Got a few more minutes.
Yeah.
You started a bit late.
Yeah. Well, I can finish there. I don't have anything further to add. I just think this is an example of a real practical problem. Definitely, it's not a toy problem at all. It's something of real need. It is the subject of FFT is one that has been tackled by pure mathematicians, Nicholson and others. So somebody knows the theory, but I think not in a general way, but I think not many people know it. And what they know is not communicated to me, at least, in a way that I can turn it into something practical. So any suggestions would be appreciated there. Yeah, that's enough from me, I think.